Hello, this is Mr. White, and this video is on limits at infinity, which we also called in pre-calculus end behavior. Here are the exercises we're going to cover in this video. And if it seems strange that we're bringing up limits again at this time in the course after we've been straying away from limits and building up a repertoire of more advanced derivative skills, well, it actually is going to transition quite nicely into integral calculus, where limits, particularly limits going to infinity, are going to once again play a huge role. So let's get to that first set of exercises. Here they are on a separate slide, all spread out nicely. And we find it easiest to take a rather informal approach with limits as x goes to either positive or negative infinity. The rather informal approach is just to imagine ourselves plugging in bigger and bigger numbers for x. Imagine x is 100, 1,000, 1,000,000, and we pretty quickly convince ourselves that these constants here become irrelevant. They become negligible as x becomes bigger and bigger and bigger in either the positive or negative direction. Now be careful. Don't cross out the 5 here because that's being multiplied by x, not added to it. So that is going to still be relevant. So after crossing out those constants, we see that what we have left is negative x squared over 5x. And if we reduce that fraction, if we divide both numerator and denominator by x, we get negative 8x over 5. And of course, we still have the limit as x goes to infinity. And we could tell that if we try once again to plug in x getting really, really big, 100, 1,000, 1,000,000, we see that this is just going to become a really, really large negative number. So we say that that's going to approach negative infinity. And we can similarly see that if the limit had been for x approaching negative infinity, if the x value had been what was going in the very negative direction, we can easily see from that expression there that the limit would then go to positive infinity. So let's shrink that result down and bring the graph of that function onto the screen and just support our results there. So we said that the limit as x got bigger and bigger and bigger, the y value would get more and more negative. And we see, sure enough, that as x gets bigger and bigger and bigger in the positive direction, the y value is getting more and more negative. Now for this other case where x is going to negative infinity, we see that as x gets more and more negative, the y value gets more and more positive, heading towards positive infinity. So graphically, our results are supported. This next exercise looks pretty similar at first glance, but we do see that whereas there is an x here, there's an x squared here. And we're going to take a similar approach. We're going to imagine plugging in larger and larger values for x because once again we have x approaching positive infinity. And so we're going to see once again that the 7 becomes negligible and the plus 1 becomes negligible. And now we look at what we end up with, and we've got negative x squared over 5x squared limit. And seeing that those x squareds really cancel out, we see that we're going to end up with just negative 8/5. And that is the limit. We see that even if x had been approaching negative infinity instead, we see that those x squareds still would have canceled out, and we still would get negative 8/5. So let's shrink that down, move it over, and once again, support graphically. And we see that sure enough, as x gets bigger and bigger in the positive direction, it levels out to some apparently constant y value, same as when x goes in the negative direction. And although it's hard to see just from this graph alone, we can believe that they are both leveling out in both directions to some number to negative 8/5, which is between negative 1 and negative 2. We also see the evidence that our decision to say that those constants were negligible really did hinge upon x approaching either positive or negative infinity. We see that for values of x that are smaller, we see that those constants really did make a difference, and they created that hump form in the middle there. So let's scroll down once again and one more time see another problem that looks similar at first glance, but whereas we just had a 5 here, it's a 5x down here. However, the same approach will still work. We can still justify getting rid of this 7 or considering this 7 and this 1 negligible. And we can still rewrite the limit as x goes to infinity. This time it's negative 8x squared over 5x cubed. And that reduces to just negative 8 over 5x. And as x gets bigger and bigger and bigger in the positive direction, as x becomes 100, 1,000, a million, we see that y value, that the total fraction there is going to approach 0. The numerator stays the same, but the denominator gets larger and larger and larger. We get a limit of 0. Same thing, if x were instead approaching negative infinity, we still would be approaching 0. Now we might make the distinction that in this case, as x approaches positive infinity, that we're going to approach 0 from the negative side. In other words, these will always be negative numbers that just become, that tend to approach 0. Whereas for x approaches negative infinity, we could say that, okay, both the numerator and denominator would be negative, so we'd approach 0 from the positive side. But rather than try to denote that, we'll just leave our answer at 0. And when we move this over and bring on our graphical evidence, we do see what I was just mentioning there. We see that as x approaches positive infinity, we do see that this graph dipped below the x-axis and is approaching 0 from below. The y values are still going to be negative, albeit very small. And we see that as x approaches negative infinity, we see that the graph is positive above the x-axis, but still leveling out to the x-axis, leveling out to 0 as we go to the left. We also see that when we look at this, we expect that there's going to be a vertical asymptote, and sure enough, there is a vertical asymptote there. No surprise. Okay, so finally, let's get to this last one here, at least for this set of problems. And let's switch it up here. I've been doing all these limits going to positive infinity and limits of a function that looked very similar to each other. Let's see how this one goes. And even though this number 1729 looks like what we might consider a big number in most everyday contexts, we have to remind ourselves that as x goes to negative infinity, negative 100, negative 1,000, negative a million, even this too will still seem very small compared to the other terms up there in the numerator. And even though this can get very big in the negative direction, this will still dwarf it. Negative 3 times negative a million is going to be very, very small compared to 6 times a million squared. So using that justification, we will cross out the negative 3x as well. Down below, we can tell that that 17 is going to be dwarfed. And what I'm ending up with is square root of 6 x squared all over x, with the limit, of course. And our next instinctive move is to say, wait a minute, that x squared under the radical, can't I bring that out of the radical? Well, yes, but we're going to have to be careful. We can bring it out and make that x in front of a root 6 over x, but we have to be careful because x is approaching negative infinity. And remember, square roots, well, first of all, let me back up. 6x squared, whether x is positive or negative, is going to be a positive number. And then when I square root it, I'm only going to take the positive root, what's called the principal root. So keep in mind that just bringing this x out to the front seems to violate that rule. And what we might do to fix it is to put some absolute value bars around it, and that would be more legit. So we'll put the limit there. And rather than just cancel out the x's, okay, there, space them apart a little bit. Keep in mind that as x approaches negative infinity, negative 100, negative 1,000, negative a million, the absolute value of negative a million over negative million itself is really going to give us a negative 1, right? So our limit is going to be negative square root of 6. Let's go ahead and move this over. And if instead x had been approaching positive infinity, then that absolute value of 1,000,000 over 1,000,000 would have just been 1 and would not have made a difference. They could have canceled each other out, and we would have gotten positive root 6. So while in most cases the limit as x approaches negative infinity is typically the same number as when it approaches positive infinity, we've seen an exception here. And when I move this over and bring the graph onto the screen, we'll see the evidence there that as x approached negative infinity, as we went to the left, we were leveling out at some y value that it looks like it's about negative root 6. Again, root 6 is about negative, or root 6 is about 2.4 something. And even though I cut off the graph here, we could imagine that as we go to the right, that it is leveling out at positive root 6. And I should point out, just in case you're checking on your calculator and are puzzled, notice that my scaling is a little different than it was previously, that I have my x-min going from negative 100 to positive 10. So, on to our last exercise. We are to sketch the graph of this function shown, considering things like extrema, intercepts, symmetry, and asymptotes, without using a calculator, of course. So, even though it's listed in the order of doing extrema first, I'm going to say let's do the intercepts first. Let's go in the order from easiest or least amount of work to most amount of work. So let's consider the intercepts. The y-intercept is what we get from a graph when we plug in 0 for x, right? And when I plug in 0 for x, I see that I get negative 25 over negative 25, so that's going to be 1. So my y-intercept is when x equals 0 and y equals 1. Okay, simple enough, right? Let's go on to x-intercepts. X-intercepts occur when we have the y value equal to 0. And so looking at that equation we have now, we recognize that the denominator doesn't really matter here. If I multiplied both sides of the equation by x squared minus 25, it would cancel out on the right, and I'd still have 0 on the left. And I need to solve that equation, 0 equals 3x squared minus 25. And that would give me x squared equals 25 over 3, which means that x equals 5 over root 3. But oh, wait a minute, we just took the square root of both sides, so I really need a plus or minus, right? So my x-intercept, I have two of them. My x-intercepts are going to be negative 5 over root 3, 0, and positive 5 over root 3, 0. And if I plug in 5 over root 3 on my calculator, I get about 2.9-ish. So if I want to go ahead and plot these points on the graph, I'll put the y-intercept here at 0, 1, and I'll put my x-intercepts just shy of 3, 0, and negative 3, 0. Okay, let's go on to symmetry. And symmetry has to do with what would happen if I plugged in positive values for x and that same value but negative. So for example, without even working it completely out, I know that if I plugged in positive 9 here, just to pick a number at random, and positive 9 here, the fact that the 9s are being squared in both cases means that even if I plugged in a negative 9, I would get the same y value. So remember how we called that an even function? It's one where if you have a graph that does something like this on the right side, you know it's going to do the exactly same thing. It's going to be a mirror image over here on the left side. So we're going to say this is an even function. And algebraically what that means is that f of negative x gives you the same result as f of positive x. And graphically what that means is that, again, it's symmetric across the y-axis. And we already see a hint of that with our x-intercepts, the fact that we saw one of them mirrored across the y-axis there. So let's look at vertical asymptotes next. We'll do that separately from horizontal asymptotes. For vertical asymptotes, we'll look at the denominator there, and we see that that denominator factors into x plus 5, x minus 5. And we see that the top does not factor similarly. It would not contain either of these two factors. If it did, we might have a hole instead of a vertical asymptote. But since it doesn't contain the same factors, we know that we have vertical asymptotes at x equals negative 5 and at x equals positive 5. And I can go ahead and depict that on the graph here by drawing these vertical asymptotes at negative 5, x equals negative 5, and at x equals positive 5. So we're starting to develop a picture. We can kind of see what's going on with this graph here. We might even be willing to venture an educated guess that something like this goes on in the middle, but we don't have much of a sense of what goes on out here or out here yet. So we move on. So let's do horizontal asymptotes next. And that really relates to the topic at hand, limits at infinity. So let me temporarily cover up the graph to provide a workspace. And horizontal asymptotes are all about what happens to the limit of the function f of x, or whatever you want to call it, as x approaches either positive or negative infinity. We'll start with positive infinity. And similar to the previous exercise, we imagine that as x gets really big, 100, 1,000, 1,000,000, these constants become pretty negligible. And then we've got 3x squared over x squared, which is going to reduce to just 3, right? So that limit will just equal 3. And similarly, if I do the limit as x approaches infinity, I would get the same result. The same reasoning would occur. Cross out those constants. 3x squared over x squared will still give us a limit of 3, positive 3. So that means we have a horizontal asymptote at y equals 3. Let's shrink that down and then bring the graph back onto the screen. And let's draw that horizontal asymptote at y equals 3. All right, the last task that we were asked specifically to do is to find any extrema. So let's go for that now. Let me scroll down here. And I've got a repeat of the y equation there. And we know that for extrema, we're going to start by taking the first derivative. So let's go ahead and use the quotient rule here. Y prime equals bottom times derivative of top minus top times derivative of the bottom, all over bottom squared, right? We distribute out the numerator, and we're going to get 6x cubed minus 150x, and distribute that negative, and get minus 6x cubed plus 50x, all over that denominator. And then we combine our like terms. So 6x cubed and minus 6x cubed cancel out very nicely, convenient for us. And then we've got negative 150x plus 50x. So that gives us minus 100x all over that denominator. So of course I'm going to set that equal to 0 or undefined. And I ask the question, what's going to make that numerator equal to 0, which would make the whole derivative equal to 0? Well, that would be when x equals 0, right? And as for what makes the denominator equal to 0, which would make the whole derivative undefined, that would be x equals 5 or negative 5. However, let's recall that that's where our asymptotes are. So remember, 5 and negative 5 are not even in the domain of the function. Therefore, they technically are not critical numbers. I can observe them if I were going to do the first derivative test. In fact, I should observe them for establishing my intervals. But as far as critical numbers go, the only one is x equals 0. Now, I haven't really committed here. Was I going to use the first derivative test or the second derivative test? Remember, both of them are for the purpose of finding extrema. But I'm actually going to be somewhat slick here, and I'm going to avoid using either test. I'm going to draw a conclusion just using some logic here. So here's my logic. This is my only critical number, x equals 0, right? And I know that these are vertical asymptotes. So if I scroll back up to the picture I've got here, I can already kind of tell that at that critical number of 0, I've already got a hunch that the graph is going to do something like this. Now we should ask the question, how do I know that it does something like that? How do I know that this, instead of being a local maximum like it appears to be, how do I know it's not really a local minimum that then comes back down and does something like that? How can I defend against that? Well, if it did something like that, that would mean that there were more extrema here and here. And we would have caught those finding the critical numbers. But we already found all the critical numbers, and there are no additional critical numbers. So that's how I'm going to defend it and say, you know what, I don't even have to finish the first or second derivative test. I know that this graph can only increase on this interval, reach a local maximum, and then decrease on this interval before riding along the asymptotes. Now, due to the symmetry, I should draw that a little more carefully. Okay, there, that looks a little better. And so to make sure I've answered all the things I was supposed to do, extrema, I would say that that occurred at 0, 1, and that was a local max. And that apparently is our only extreme. Now, ultimately, I was supposed to sketch what this graph looked like, right? And even in spite of doing the intercepts and the symmetry and the vertical and horizontal asymptotes and extrema, never really did get a sense of what's going on over here for sure. We could tell there's going to be horizontal asymptotes, but we don't know whether it does this or something other than that. So if we really wanted to be thorough, we would go completely through a process called curve sketching, and we'd continue to analyze this function for things like domain and range, continuity and differentiability, increasing, decreasing intervals, concave up, concave down, inflection points. I'll spare you from that right now, but I just want to point out that we do have the knowledge, we do have the skills to tackle all of that, and that would help us determine what the rest of this graph looks like. What I'm going to do instead, just it's a bit of a cop-out, but I'm going to go back to our original equation, and I'm going to do a quick calculation. Turns out if I plug in the number 6 here and grab a calculator and compute it, I get something that's approximately equal to 7.5. Now, why did I do that? I did that so that if I graph that point now, if I go 6 over and 7.5 up, I land somewhere right around here. And that's the clue that I need. I know that I've got a vertical asymptote and a horizontal asymptote nearby, and that's the clue that I'm going to use to say, okay, the graph does something like this. And due to the even symmetry of this graph, I know I've got a mirror image piece over here that does that. Have I actually proven that it does that exactly? Not really, but we're going to say good enough for now.